Okay, so today we are going to continue our discussions on the flash. And last lecture we talked about the Noflash operation and Nonflash operations. So today we are going to have a comparison between those two flash technologies. So in terms of the applications, so here this is a brief comparison between NAND and NOR. So basically, NAND has larger capacity, so you want to use that for massive data storage. So like your camera, MP3, phone, tablet, SSD, so you store your data in the NAND flash. And Noflash is mostly used for the code storage. So you have some firmware where you have some boot up code. You may store that in the Noflash because Noflash you can read out pretty fast. Therefore, you want to use that to store your execution, the code for the program execution. So here, those are the products that may use the Noflash. So as the NAND flash is becoming more and more popular, so actually NAND flash is also taking the space of the traditionally Noflash applications. So the NAND flash actually is going to expand their applications more towards the NOR. Therefore, the NAND flash takes up the market more than 97-98% in terms of the revenue. If you look at the NAND flash versus Noflash.
Professor, excuse me, you're not sharing your screen. We are not able to see it.
Oh, sorry. So.
Oh, no problem. Thank you.
All right.
Yes.
So the screen is now shared. Thanks for the reminder.
Yeah. Thank you.
So here basically we compare the Noflash and NAND flash. And here the NAND, of course, will be the focus of this course as it becomes the mainstream of the flash technology. So here in this table, we briefly compare the key metrics between the NAND flash and Noflash. So as we just mentioned, the NAND flash is good for the data storage, for your like pictures, videos, audios, your data. And the Noflash is good for code storage, where you can have a random access, and you can also read out fast. So if you compare the metrics, the Noflash roughly about 10F square in the cell size, and the NAND flash, here we talk about the two-dimensional NAND flash with a single level cell. So this is a basic NAND flash. If you do that, you have the 4F square as we discussed earlier. And then the MLC, so this is what we are going to discuss in the next. So this is how many bits you can store in one cell. So in general, both Noflash and NAND flash can store like multiple bits per cell. And NAND flash you can store even more bits because you care about the density. So here we push for the MLC capability. So the key difference between NAND flash and Noflash is this random access. So this random access, especially for the read. For the Noflash, as we discussed before, all the floating gate transistors are connected in parallel. So they are like a DRAM. So you can address individual cell in the Noflash array. But for the NAND flash, if you recall, the floating gate transistors are in series. So you cannot address individual floating gate transistor without avoiding other transistors. You have to enable the selected cell, and then you have to apply this V-pass signal to turn on all the unselected cell because the signal needs to be read out in series across those transistors. And also the Noflash, the program is by the channel 40 electrons, and flash, NAND flash, F internally. So here, in terms of the latency, here this is key difference. Noflash, 50 nanoseconds, and NAND flash maybe larger than 10 microseconds. And the write energy, also the Noflash is much higher. This is because the channel 40 electron, as we discussed before, you need to pass large drain currents. Therefore, the programming efficiency is low because 1 out of maybe a billion electrons can go into the gate stack. So endurance-wise, this is what we are going to discuss in the next. So Noflash generally may perform better in terms of a number of cycles you can write the data in. So this is the general comparison between the Nonflash and Noflash. So the key difference is in this read speed. If you need high read speed, especially in the actually for the Nonflash, here I will have to emphasize this read latency is for the to read out the first page. This is a random read latency. But once you enable the first page, then the following page readout actually can be pretty fast in terms of latency. This is because the I/O design for the Nonflash, you can still use something similar like the DRAM's DDR, so you can prefetch more bits and then burst out. So you can improve the latency for the readout for the Nonflash through the I/O technique. But the first bit to read out, you have to wait for like 10 microseconds. This is what you cannot avoid in the Nonflash. So if you really think about the Nonflash, the reason is that you have these transistors in series. If you select this cell to read out, you have to apply the way-pass read for the other cells. So this cell, the current will go through those like series resistor of those channel resistance, and then to the BL, you have BL cap. So there is a non-RC delay from this selected cell to your sense amp. So the series resistance from the drain will limit your RC readout performance. This is unlike the Noflash because each transistor is in parallel to each other, right? So this is to your like sense amp. So you can directly access individual transistors to the sense amp without going through other transistors. But for the Nonflash, you have to go through other transistors. That's why the Nonflash is slower in the initial readout speed. And here, if we compare the capacity, Noflash generally lower capacity in terms of the bits, number of bits. The largest Noflash maybe like 1 or 2 gigabits per chip, but most of the Noflash is below like 1 gigabit. And Nonflash, you can have up to like 1 terabit. If you convert to bytes, then that will be like 128 gigabytes per chip. So this is enabled by the MLC multi-level cell capability, as we discussed later. And also the 3D Nonflash will further boost the capacity because you can pack more bits vertically in the third dimension. So we will discuss that in the next. But basically, the Nonflash has much larger capacity than the Noflash. Noflash typically like below 1 gigabit. Nonflash can be 1 terabit. So this is like gigabit level to the terabit level. So here we use bit. If you convert to byte, you know you have to divide by 8. And here the write performance, as we discussed, because of the programming method is different. Noflash uses channel holding electron, so you have to pass large currents from the drain to the source, or electrons from the source to the drain. So only a very small portion of the electrons can go into the gate. Therefore, they are called lucky electrons. And you have, for example, you may have to pass 50 milliamp to program the Noflash. So the current is large, therefore the power consumption is large for the Noflash. For the NAND flash, we rely on this FN tunneling. All the electrons in this substrate will vertically tunnel into the floating gate as FN tunneling. So the gate current for programming is pretty small. For example, 1 picoamp, 100% of the electrons go into the gate. The efficiency is high. So here the current is low, therefore the power consumption, is voltage times current will be low. And here we summarize this random read performance. Actually, we already briefly discussed before. So the Noflash, because all the cells here you see that they are collected in parallel, so you can have direct access to individual cell from the bit line, and bit line will connect to the sense amp. And the NAND flash, so all the cells are in series, so you don't have individual direct access to the individual cell. You have to go through this stream. Therefore, the speed, read performance will be low for the NAND flash. And here we also show the layout. You see the difference between those two. For the Noflash, because you have to accommodate this individual contact to the individual transistors here, therefore you have to have this contact region. And to save the space, you can have two floating gate transistors share one bitline contact, similar as a DRAM. But anyway, you have to insert this contact region between those floating gate transistors. So you lose some space due to the contact. It's less compact. The NAND flash, the reason to get high density is because you get rid of those contacts within the string. So within the string, you don't have any contact. Only at the end of the string, you have this contact to the bit line and the source line. So you only have the contact at the end. Therefore, you can have much more compact layout for the NAND flash. All right, any questions for this summary between NOR and NAND? If not, then we will move on. So here I just want to have some discussions on the NAND flash translation layer. It's also called FTL, flash translation layer. This is because the NAND flash does not have the direct access to the individual cell, as we discussed earlier. And also the NAND flash uses block-based erase and page-by-page program mechanism. Therefore, there is a mapping between the logic address to the physical address. So if you look at the SSD system, so here typically you have to follow some file system format, and then your host or your processor or the DRAM will go through this file system format to talk to the flash. So on the flash, there is a controller, and this controller will contain this flash translation layer, FTL, which will do three jobs here. First is the address mapping. So this is to convert the logic address to the physical address on the flash blocks. And then also this will do this so-called garbage collection. We will discuss that in a minute. And also the wire leveling. So this is to uniformly distribute the write operations into different blocks. And we will discuss that in a minute as well. So this FTL is a unique module in the flash controller, NAND flash controller. And we will discuss that in more details in the following slides. So the basic idea is that if you have a logic, if you think about your logic space, your program, your software program will have the address for your data in the logical space. So for example, here you may have your pictures, videos occupy some consecutive space in the logic address. But when they store in the Nonflash, they may not be continuous or consecutive in the physical space. So you need to have this logic to the physical address mapping through this FTL. And also this FTL will analyze the frequency you fetch the data. You can categorize the data to be hot data, warm data, and cold data, and then therefore you can map them to different blocks. So here this arrow basically shows how you map the data from the logical space to the actual physical space in the Nonflash blocks. And we will discuss the operations in more details in the following slides. But here basically there is a logic to physical address mapping. And this is due to the block-based erase and page-by-page program mechanism of the Nonflash. We will discuss in more details using this example. So here we are going to show one example. You are going to write the last page of a block in Nonflash. So think about here is your data. And you want to write this data to the logic block address at 2K. This LBA is logic block address. So here in the FTL, you will have a mapping, this map. You have this map. So on the logic space, so here every time you write the data in the length of 2K, 2 kilobytes, so you will have the logic space, first 0K, 2K, 4K, 3 groups. So those are consecutive in the logic space. For example, those 3 blocks may contain your picture. But you have to store that. You may have to store that in different blocks in the physical space. So here is on this mapping, it says that logic address 0K is stored in the block 5. This is physical block 5, number 5. And all the 2K is on the physical block 0, 4K is on the physical block 0. And here on the physical space, there will be a pointer. This is a right pointer. As we discussed before, so the program is page by page, and then you have this pointer. Page by page means that the pointer has to move page by page, or word line by word line. You cannot jump from one word line to another arbitrary word line. You have to follow the order of the page. So this is the right pointer, and it is in this case, right now it's in the block 1. Sorry, I believe it's in the block, let me see. So it's in the block 0. Let's see. So I think this at this point is at block 2, at end of the block. So here, the erase, as we discussed before, will erase the whole block. So the whole block, if it's erased, that means it will be all ones. And then if you have a right pointer here, so what we are going to do is to flip some of the ones to 0 by programming, right? So you may flip some of those to 0 depending on the data from outside. So this is what you will do for the programming. So in this case, we want to write this data to this logic block address 2K. And previously, I believe the 2K stored in the block 0. Now you have to write the new data in this LBA2K. So you have to, but you cannot arbitrarily write the data you have to write the data to where the pointer currently locates. So right now, this pointer is at the end of the block 2, page 63. So here, one block, 64 word length, so 64 pages. The last page is page 63. So here you have to update basically you have to write the LBA to the current pointer, which is at block 2, page 63. So this new data will be written into here. So this page, before writing, you have all ones, right? And then you have to write this data, flip some of them by programming, and unselected columns will be inhibit, as we discussed before. So basically, you have to write this new data into this block where the pointer currently locates, and then you update the information in the mapping. So now you have to record the 2K is stored in the current pointer, which is block 2, page 63. So you cross out the previous mapping information and then update with the current pointer's address. Now your pointer move to the next one. So now because it's at the end of the block, so after this write operation, the pointer will move to a new block. So then in this example, it moved to the block 1 and the first page of the block 1. Meanwhile, here you have to update this block information table. So this one basically record the block's information. For example, after you do this, you have to reduce the valid page count in block 0. Because this block 0, this logic address used to be stored in block 0. Now you move to the block 2. So the valid page count in block 0 will reduce by 1. So here it will reduce by 1. And meanwhile, the block 2, now you have a new data right in. So the valid page count will increase by 1 or become 5. So here you see that in the previous block 0, the data is still there. The previous data, LBA 2K, is still there. But now it becomes invalid because the data is still there. You didn't erase that. The data is still there, but the data is not useful. So it becomes garbage. So basically, the data in the block 0 has no mapping, no corresponding logic space data. Therefore, the page in the block 0 becomes invalid. So this is the example for write to the last page of the block. Any questions here? Yes. No. So this is not erase. This is a program, right? So block 2 previously stored some 4. In this example, the block 2 stores 4 valid page already. And then you move to this here. So the block 2 is not a new block, I would say, in this case. In this case, no block erase. And we will show one example, there will be a block erase in the next. So you have to decide when to erase the block. So when the valid page count reduced to a certain level, then you have to erase that block. We'll discuss that in a minute. So here we write a new block. So here this is in block, I believe block 1. So this is a new block, and the block 1. So now we move to the let me see. We move to a new block, oops. This block 1 is a completely new block, so it's all ones. Now the pointer moves to the first page, and then we write new data to logic space 4K. This is new data. So here then we have to mark the block 1 now erased become false because you start using that. And then we update the valid page count from 0 to 1 in the block 1. This is block 1. And then the old data where the 4K used to store is block 0. Then you have to reduce valid page count in block 0 by 1. So 14 becomes 3. So then this is you continuously write the data from the logic 2K to 4K. Now it's physically located in the block 1, page 0. So here, let's talk about the erase. So if one block, after you move around all the data, this block may not have enough valid page. For example, here, the block 2 only has 3 valid page. So that means that still there are many data in the block 2, but only 3 of them are valid. That means 3 of them have the corresponding logic address. The others are garbage. So the block 2 is not very useful. So we want to erase the block 2. But before erase, you have to do one thing, that is a garbage collection. So here, there's still some 3 like valid page. You don't want to lose that data. So before the erase, you have to write those, you have to move those 3 valid page into the new block. So for example, right now, you have the new block where the current pointer locates, and then you have to read out those 3 valid page, and then write those 3 page data into the pointer where the pointer locates. And after that, then you erase the whole block. After you erase, this become all ones. The whole block become all ones. So here then you need to update. Here the valid page count 3 becomes completely 0. And then after erase, then the erase indicator or flag will become true. That means here in this block is all ones. And also you need to update the erase count of this block. It changed from 0 to 1. You have erased once. So this erase count basically record the endurance, how many cycles you have erased that block. As we discussed later, the Nonflash has certain lifetime. You cannot erase too many cycles. So you have to remember how many erase cycles this block has gone through. And the FTL will also do the wear leveling. The wear leveling. This is to distribute the program and erase operations uniformly across all the blocks. You don't want one block to be heavily erased. You want to, let's say, the eraser count. You need to look at the eraser count for different blocks. And if you need to erase, then you have to consider which one to erase to balance the erase count across the blocks. So this can improve your lifetime. If you heavily use one block, that block will become dead eventually. So you don't want to do that. So this FTL, this block information table, will help you to determine which block to erase. So there are many considerations in the controller design. For example, you have to keep certain number of blocks erased in the Nonflash, in the SSD, because the SSD will have no idea how much data you want to write consecutively. For example, if you want to record your video, right, for like 1 hour, then you have to make sure there's enough space. That means enough erased block available for you to record such long video. So you have to do some like analysis of the block information table, and then prepare enough space in case your application will write a large chunk of data at one time. So there are many design considerations of the Flash controller and so on. So we will not go into the details there. Question? So bad block means that block has been heavily used and become bad, become not useful. And sequence number, actually, I don't know what is that, to be frank. So you can ignore that for now. So if you really think about this very complicated operation, it comes from the Nonflash operation because it's a block-based erase and page-by-page programming. So once you erase, you have to erase all of them to be one. Therefore, you have to collect the garbage and transfer. And then you have to have this mapping because the write pointer will do this write operation one by one from page to page. So you cannot move around. So that's why you have to have this mapping from logic space to the physical space. So this operation is really determined by the Nonflash mechanism, as we discussed before, the program erase. It's not very random access, so you have to follow certain order. It's not random, it's not like DRAM, you can go to arbitrary location and fetch the data from there. Nonflash is not like that. Yes. Yes, so here I think this example we haven't indicate where the current pointer is. If it's in the block 1 current pointer, yes, then the valid page count number will increase by 3. But here in this example, we didn't specify where the pointer is. It's maybe in the block 10 or somewhere. And let me see if there's any questions online. No, then let's move on to the MLC, multi-level cell. So this is also a new feature in the Flash compared to the SRAM and DRAM. You only have a single level cell. So the multi-level cell basically means you can store multiple bits in one cell. Cell means here one floating gate transistor. So the way you store multi-level is to engineer the threshold voltage. So the single level cell here, we show the VT, the threshold voltage distribution. And in one array, due to the variation, so you will have a spread out of the distribution of the threshold voltage even after you program or erase. But anyway, you have two groups, two distribution. So one is for the lower threshold voltage. This is for the one state or the program, the erased state, and the other one is in the program state. So if you recall the IDVG curve we showed before, right? IDVG. So you have two threshold voltage. this is programmed, this is erased. But due to the variation, different transistors may behave a little bit different. So here you may have a spread out of the VT distribution. So here we show this distribution in one array typically. So if you measure the floating gate transistor, for the program state, there will be a distribution. For the erased state, there will be a distribution of the VT. So here we plot this VT distribution. And the single level cell only have two states, and then you can encode 0 and 1 like this. But you can insert more VT states. So here that means in the IDVG curve, if somehow you can manage to have this kind of IDVG, right? So you have different VTH states. Oops. For example, if you manage to have 4 levels, and each will have some distribution around the mean value. If you have 4 states, then you can call this multi-level cell, and this is 2 levels. Actually, there's a typo. 4 levels. This is 2 bit per cell. And if you have 8 levels of the VTH, then you can encode 3-bit information. So here, the 2 bit per cell is typically called MLC. 3-bit per cell is typically called TLC. This is triple level cell. And today, for the advanced NAND flash, you may have the QLC. This is quadruple 4-bit per cell. So here, the MLC, narrowly speaking, it only refers to this 2 bit per cell. But in general, if we say MLC, in a broader definition, it includes all kinds of multi-bit per cell. But in the NAND flash context, by convention, the MLC refers to the 2 bit per cell, and TLC is 3 bit per cell, QLC is 4 bit per cell. And one more thing I want to emphasize is on the encoding of those levels. So for the 4 levels, 2 bit per cell, so this is one of the typical encoding method. You look at those 4 levels, and you need to assign those 1, 1, 1, 0, 0, 1, 1, 0. So let me ask the question. You look at here, this is 1, 1, the second is 0, 1, this is 0, 0, this is 1, 0. Why not we do this way? 0, 0, 0, 1, 1, 0, 1, 1. This is more logically, right? So if you think this is like 0, 1, 2, 3, right? In the binary format, why not follow this order? Any idea? So this is when we do the encoding of the data. What we show here is the typical encoding. So we put basically we put 0, 0 here and 1, 0 here and 1, 0. Sorry, 0, 1 and 1, 0 like this way. Why is that? Any idea? Sorry, I couldn't hear you, but okay. So let me just tell you. Okay, the key consideration here is the error probability. So you want the Hamming distance between those coding differ by 1 in the adjacent levels. So if you somehow have error, right, so due to the variation or some reliability issues. So for example, if this one somehow the tail bits cross this middle reference, then you have 1 error. Then you only want to have 1 bit error instead of 2 bit error. So let's do the conventional way. If you have this kind of mapping, right? If you have this crossover, then your data change from 0, 1 to 1, 0. Then that means 2 bit error. But if the Hamming distance between the adjacent levels differ by 1, then you only have 1 bit error. And similarly, you can check this 3 bit per cell, the encoding, and I believe the adjacent cell differ by 1. All right, so this is the basic idea of the multi-level cell. Then you may wonder how we read out. So basically, we can have different multi-level kind of sense amplifier. So you can have some reference between the adjacent levels, have some reference cell between the adjacent cell. If you have a single level cell, then you have the program state and erase state. This is IDVG, right? So if you have some reference in the middle, then that will help to determine your current is larger or smaller than the reference cell. And similarly, if you have more levels, then you can have the multi-level reference to determine whether which VTH state this device belongs to. So you can use the multi-level sense amplifier to determine the corresponding levels. And after that, you can do this encoding following the mapping here. So you have to change from the decimal values 0, 1, 2, 3, 4 level to this encoded binary format following this kind of encoding. So there are some digital circuits you need to do the encoding. Okay, so then let's talk about what makes the VTH tunable. Because essentially the multi-level cell or the MLC, TLC, QLC rely on the VTH distribution, and you want to create more levels in the VTH distribution. So basically the VTH of the floating gate transistor can be modulated by this programming time and programming voltage. So here we show the VTH initially after the erase, typically is negative value, like negative 2 volts in the Nonflash. And then you can increase the VTH by controlling the programming time and also the programming voltage. So if you fix the voltage, like the 17 volts, if you increase the programming time, your VTH will gradually increase. And then if you fix the programming time, then if you increase the voltage, the VTH will also increase. So you can control the programming time and programming voltage to achieve your target VTH level. And let me ask the question. Why would the VTH increases with more programming time or larger programming voltage? What physically determines the VTH? Any idea? So what is the physics behind this behavior? So if you recall the principle for the floating gate transistor, we inject the electrons in the floating gate. So the number of the electrons in the floating gate determines the VTH shift. If you recall, we have this equation, delta VT equals to the QFG divided by the CK. This is in one of the earlier slides. So the number of charges, in this case electrons, in the floating gate divided by this interpoly dielectric capacitance determines the VTH shift, that is this delta VT. So the more electrons stored in the floating gates, the higher the threshold voltage. So by longer programming time or higher voltage, you inject more electrons into the floating gate. Therefore, you can control the VT. So typically, the range for the VT tuning is from like negative 2 volts up to like 4 volts or 5 volts in the Nonflash floating gate transistor. So you can insert multiple levels in between. if you do 3 bit per cell, so let's say in total you have like delta VT, you have around 6 volts. And then if you do 3 bit per cell, you need to roughly divide this into 7 bins, 7 segments. So like 0.8 or 0.9 plus 2.9 volts per level. I mean the distance. So you still have some space. But of course, we need to consider the distribution. But let's say the mean value, you have like close to 1 volt per level, the distance between the mean value of each level. But we have to consider the distribution. It's not just the mean value. There will be variations across the transistors, and also during the programming, there will be inaccurate programming because you cannot control very accurately on the electrons, right? So it's a statistical process for the electrons to tunnel through. So there will be some variations in the VT. Even you use the same programming time, the same programming voltage, and if you do this on different devices, or even if you repeat this on the same device, you may end up with different VT, a little bit different VT every time. So that's the distribution. So here we have to tighten the VTH distribution, right? So think about it. So you have those mean values, and we just said that the mean value distance may be 1 volt. You have to make the distribution very tight because you don't want the tail to cross over. Therefore, you still have some margin between the levels. So we have to tighten this distribution. And the way to tighten the distribution is typically called this ISPP. This is the incremental step pulse programming, ISPP. So the idea is to write and verify. So first you apply like a relatively low programming voltage, in this case like 16 volts to start with. After the first program, then you read and verify. So after the first program pulse, then you read out and then you compare to your target, the VTH. Of course, eventually you compare like a readout current. So you compare with your target. If it's below your target, because this is a monotonic increase. Okay, every time you do this pulse, your VTH will increase a little bit. So first you apply first program pulse and then verify, read it. If it's still below the target, you apply the second pulse. So then the second pulse here, typically you will increase this by a delta V program. So you have this like a increasing pulse amplitude every programming pulse. So you try to approach your target gradually by increasing the voltage each pulse. So if you do that, then you can tighten the distribution. So here, of course, you don't need to do this. You can apply constant voltage, multiple pulses. But if you do that, here this experimental data show you that if you use a constant 6.5 volts, you can get a very tight distribution like this. So here this measured from like a million cells in the array. So typically when you do this kind of experiments, you have to program the whole array like a mega or even tens of mega cells. So here that's why you have the number of cells or the count. So here you can get a very tight distribution by a constant program. But for this one, if you keep doing this, you may need like up to 37 cycles, program and verify cycles to achieve this. If you increase the constant voltage to 18 volts, then you will have very wide distribution. But if you do this gradual increase, then you can get a relatively good distribution only within 2 to 6 program and verify cycles. And this is a much shortened write time. The flash write program is already slow. If you do many cycles of this verify, it will even slower down your programming speed. So you want to shorten this verify cycles. So this ISPP is a good way to balance the programming speed and also in terms of the distribution tightening. So this is widely used in today's Nonflash, the ISPP. So here you can imagine for more levels, you may need more like verify cycles. So here we just show the typical programming time for one page, because you program word line by word line, page by page, right? For the SLC, because you only need to verify one level, so you can do that within like 100 microseconds. If you do MLC, TLC, QLC, you see that the programming time increases. So like 200 microseconds, 500 microseconds, 2 milliseconds. So this is a trade-off between the density and the speed of the program. So like a QLC, you have higher density because one floating gate transistor store like 4 bits per cell, but you need to use longer time to verify those 4 bits are accurately stored in the transistor. And here we show the programming sequence for the MLC and TLC. So here we can divide that into intermediate steps. You don't need to do it one shot. So here, for example, for the 4 levels in the MLC, 2 bits per cell. So we start with the erased cell, and then we can program, depending on your data pattern, you need to store some of them, as we discussed earlier, flip from 1 to 0. But this is MLC, so actually you need to flip 1, 1 to those like 1, 0, 0, 0, 0, 1, depending on your data pattern you want to write. You don't need to jump from the erased state all the way to those final pattern at one time. What you can do is to program into this intermediate step, and then if you check your data pattern, if your data pattern, let's say, the first bit is 0, then you only look at your data pattern, the first bit, MSB. If it's 1, you will maintain those cells in the erased state in the first intermediate programming. You don't do anything. If your data is 1x or 0x, I should do this way, I think. So then if it's 0x, we don't care about the second bit. Then for those data, you need to program that into some intermediate step. So here this is the intermediate distribution. And in the second step, then we fine-tune those distribution. So for 0x, then we need to look at what is the x. If x is 1, then we further program to this final distribution. If it's 0, then program to here. Similarly, for the 1x intermediate step, we look at what is the x, then program to the final distribution. And for the TLC, it will become even more complicated. So, but you can follow this order. So you first have some intermediate state for the 4 higher levels, and then you binary program first into 2 distribution, and then you split 1 distribution into 4, and finally we need to tighten the distribution. So here we've divided into intermediate steps, and then finally we tighten the distribution, make sure there's margin between the levels. So the TLC and QLC will have very tight margin between the levels. you may only have like 100 millivolt or 200 millivolt as a gap between those cells. So it's very challenging to have the PLC and QLC. So any questions here? One question from the chat. For ISPP, what if VT is already too high? If VT is too high, you will not have the VT too high case, because here for the ISPP, we always start with lower programming voltage. You gradually shift the VTH from low to high. You will not have an abrupt jump to a very high value. So you gradually approach your VTH. So it will not have a sudden jump to a very high value. Therefore, you cannot do anything with a high value. So you always try to be more conservative. Start from the low values first. So one more thing here, since you asked this question. So if you really have this unfortunate, like very high values after one pulse, then you cannot bring it back. You have to live with it. You have to mark it like invalid, or somehow you have to deal with that. Because in the MLC and TLC, you cannot arbitrarily move those levels. For example, here you have A, B, C, D, E, F, G. So somehow you overprogram to F, and you cannot bring it back to E. So this is not possible. You have to erase everything if you want to restart. You have to erase everything. So you cannot jump arbitrarily between the levels. There are some order for the programming to follow. Okay, next we will discuss the reliability issues for the flash. So this is also new compared to the SRAM and DRAM. So the flash memory reliability, and this will also apply to the later discussions when we talk about the other emerging non-volatile memory. So basically for the non-volatile memory, you will have those issues. First is the endurance. We already mentioned this a few times. So this means how many cycles or how many times one can program and erase the flash cell before the memory window, the VTH difference between the program erase state collapse or the window closure. So basically how many cycles you can program and erase the cell before it becomes dead. Becomes dead means you cannot distinguish program and erase, because you cannot enlarge you cannot have the VTH window between the program and erase. And the retention, this means how long the data can be returned. In floating gate transistor, that means how long the charge can be returned in the floating gate, and how long the memory window can maintain, like 1 day, 1 week, 1 month. So this is the data retention. And program read disturb. This is when you program and read the selected cell, we may have some disturb on the neighboring cells. So the neighboring cells VTH may shift undesirably. So we will discuss that one by one. The endurance means how many cycles and PE cycles, program and erase cycles, you can do on the flash transistor. So here we show some data of this SLC single level cell. So here we typically show this endurance cycle in the log scale on the x-axis. So this is how many cycles you program and erase, and one pair means 1 cycle. Program and erase is 1 cycle. And then you record the VTH state of this program. After this program and erase, you look at the memory window. This is your delta VT, right? This is the memory window. So here, typically you will not read after every cycle, because 10 to the power 6 is a large number, is 1 million cycle. So sometimes you just check at some certain checking points. So here, between those points, you still apply the program erase pulses, but you don't read out. You don't read out, therefore you don't have the record. Only at those checking points, you will read out the exact value of the VTH state. Or in other words, you read out the exact current, and you can back calculate what is VTH state. So here you see the general trend is that at the end of the programming and erase cycle, here the VTH will become smaller, the delta VTH. And typically the erased state, the VTH will become higher and higher. And this is because of the electron trapping effect. So during the program erase, the electrons go in and out through the ternal oxide. So the ternal oxide may get damaged somehow. And the electrons may be trapped into this ternal oxide. So this is the silicon substrate, and the other side is a floating gate. And in the middle, you have this ternal oxide. The electrons go in and out, but somehow the electrons may get trapped into the floating gate. In the ternal oxide. And they get trapped. So if electrons get trapped, then the VTH will increase. Because if electrons get trapped, it's more like you couldn't completely erase, right? If electrons, this is the ternal oxide, and this is your channel substrate, and this is your floating gate. So ideally for the erase, you want all the electrons removed from the floating gate. But somehow, some of the electrons get trapped into the ternal oxide. It's similar as your erase is not complete, right? You still have something in the gate stack. If you have some negative charges in the gate stack, that means VTH increase, as we discussed before. That's why here the VTH increases over the cycling. So the quality of the ternal oxide degrade over the cycling, and then the electrons get trapped. So basically there are some defects in the ternal oxide, and the defect will capture the electrons. So this is a major concern for the endurance degradation. After the cycling, the major effect is the electron trapping. That will increase the threshold voltage. Therefore, the effective window will be reduced. So this will affect not only the SLC. SLC actually have larger margin. Think about the MLC, right? You have multiple levels in between. Now your total margin, total window, shrink. You may not maintain those 8 levels in between. So the multi-level cell will have worse cycling endurance than the single-level cell. Because single-level cell you still have a large margin, even though you shrink this window, but still they are distinguishable. But think about multi-level, you have very tight margin between levels. And second is the retention. So retention means how long the data can be retained on the floating gate. So here, for the program state, you have those electrons in the floating gate. And then after cycling, as we discussed, some of the electrons may be trapped into this ternal oxide. So this will be a problem if we have high temperature on the chip. For example, if you bake the chip intentionally, or if you use it in like Arizona, for example. So after the high temperature, those captured electrons may detrap. So this captured electrons in those trap site is not very stable actually. So you can release those electrons by high temperature. So if they jump out from those trap sites, then your VTH will be lowered. And that means your data may be lost if you rely on those electrons to maintain certain VTH level, and now the electron is detrapped, then you may lower the VTH, and then your data may be changed. Especially think about the multi-level cell. You have very tight margin, right? If you release some electrons from the trap site, then the VTH decrease. As we discussed before, like the mean value only has a 1 volt difference between the levels. And think about the tail bits, then this is really a dangerous situation. So here we just show the band diagram. Before the bake, you have some trapped electrons in the ternal oxide. After bake, then the electrons released from those trap sites. And then for the retention, there are more mechanisms to cause this charge loss. Besides this detrapping, so there will be intrinsic charge loss. This is even without the trapped electrons in the ternal oxide. Even the electrons are stored in the floating gate. Even in the fresh sample, you have the electrons in the floating gate at very high temperature due to the thermal vibration. So the electrons may jump out from the floating gate due to the thermal vibration, especially at higher temperature. So this is due to the intrinsic charge loss. This is thermally driven. At high temperature, your Nonflash will tend to lose your data. And there will be extrinsic charge loss mechanism. So this is after the cycling, as we discussed. We have those traps, also defects in the ternal oxide. So those traps will assist the electrons to leak from the floating gate, because this is like a stepstone for the tunneling. This is called the trap-assisted tunneling. So if without those traps, the electrons very hard to tunnel through because this tunnel barrier is very thick. You have like 8 nanometer, 9 nanometer. Now you have those traps, so it's like a stepstone. So the electrons will tunnel to the first trap, and then from the first trap to the second trap, and then it will be easier for the electrons to tunnel through. So the electrons may leak through those traps, and this will also be shown as this SILC, so-called the stress-induced leakage current. So if you show the gate current versus the gate voltage, or if you translate to the oxide field, so you will see this like increased leakage current. If you have the program erased many cycles, you have those traps, then it will be easier for electrons to tunnel through. So you have higher leakage current. So this leakage current will remove the electrons from the floating gate, and then you may lose your data. So here we show the distribution for the data retention, like a threshold voltage shift. So here the original, this is MLC, 2 bit per cell. Those are the original distribution of those 4 levels, but the red ones are after some time, after the retention degradation happens. So for example, the detrap will move all the VTH distribution to the lower value. So you see that this distribution moves to the left, all of them, because the detrap will uniformly lower the VTH. And the SILC, the effect will be a little bit different because SILC depends on the voltage direction. So if you are in the program state, then the tail will shift towards the left. But if in the erased state, so because this stepstone can assist either electrons move out, or if you reverse the voltage in the erased state, or it will assist the electrons to move in from the substrate to the floating gate. So therefore the SILC will increase the erased state VTH because this stepstone can be bidirectional. You can assist electrons come out or go into the floating gate depending on the polarity of the voltage. So any questions here? Okay, we still have 4 minutes, so let's finish those 2 slides. So the retention is very thermally sensitive. So typically we can use this temperature acceleration test to evaluate the retention behavior. And this can be applied to other non-volatile memories as well, as we discuss later. So this is a generic approach you want to know to evaluate the retention. So basically here we bake the samples at a very high temperature to accelerate the retention because we cannot wait for like months or years to determine whether this product is reliable or not. And as an engineer, test engineer, reliability engineer, you have to identify whether your product meets the specs or not within like a few days. So here what you need to do is to apply very high temperature. This is higher than normal operational temperature. For example, 300 C or 200 C or 250 C, you vary the temperature and then you monitor the threshold voltage change over time. And then it may have this kind of degradation. Of course, higher temperature, the degradation happens faster, so the VTH shift faster. So here the idea is to determine a failure criterion. For example, here the VTH shift by like 2 volts. This is just an example. According to your application, if it's MLC, maybe you shift by 500 millivolts, you have to call it a failure. But anyway, in this SLC case, we define this like you change by 2 volts as a failure. So then you can get the time to failure in those 3 temperatures. And then you replot the data on the right-hand side. This is called the Arrhenius plot, or 1/kT plot. This is widely used. So what you will do is to look at those 3 time points and plot it in the log scale of those 3 time points. For example, maybe here and let's look at maybe those 3. So those 3 points corresponding to those 3 points. And then you have to convert the temperature from the Celsius to the Kelvin, and then do 1/kT, and convert the Kelvin to the KT unit. KT is the Boltzmann constant times the Kelvin temperature, and that is the electron volts. So you have to do this conversion to 1/kT, and then you will plot those 3 points. This will be a straight line because any degradation is following this kind of a distribution, KT over EA over KT. So this is a thermal activation function. So if your retention time is following this formula, then you can do this kind of extrapolation. The slope will be the EA. The slope will give you the EA. And if you do that, in this case, it's about 0.66 EV. So you use that to extrapolate to the lower temperature. because here those 3 points corresponding to 300C, 250C, and 200C, but you want to know your lifetime in the lower temperature. So here on the y-axis, this is the time to failure, and here the 10-year. You need to know this number is 3 times 10 to the power 8 seconds. So then you draw a line here. If your target is 10 years lifetime, so here in this extrapolation, it tells you that it can sustain the high temperature 114 degrees C over 10 years. So this is good. So you will use the higher temperature to extrapolate to the lower temperature. This is a key point of this 1/kT plot. So any questions? If not, then we will stop here.